Hello, science fans. Today, let's explore a cosmic mystery. Why is space so cold when the sun is so hot? Our sun is a giant fiery star. Its core reaches about 15 million degrees Celsius. This blazing ball sends heat and light across the solar system, making life on Earth possible. But space itself? It's freezing, about minus 270 degrees Celsius, nearly absolute zero. That's colder than anywhere on Earth, even Antarctica's harshest winter. So, here's the puzzle. If the sun is like a massive bonfire, why doesn't all of space feel warm? Stand near a fire, you feel its heat. The sun is the biggest fire around. Shouldn't space be toasty? This question helps us understand how heat works, not just on Earth, but everywhere in the universe. The answer reveals just how unique our planet is. It's a journey into energy, temperature, and the very nature of the cosmos. So, let's put on our thinking caps and dive in. We're about to solve the mystery of the hot sun and the cold, cold space. Ready? Let's get started. Visual: sun blazing, Earth basking, deep space in darkness. Visual: thermometer plunging in space. Visual: bonfire versus sun comparison. Visual: Earth's atmosphere glowing. Why is space so cold when the sun is so hot? To answer this, we need to know what heat really is. Heat is energy, the motion of tiny particles called atoms and molecules. When something is hot, its particles move fast. When cold, they barely move. Temperature measures how fast these particles jiggle. But here's the catch. Space is almost empty, a vacuum with hardly any particles. On Earth, air is packed with billions of particles in every breath. In space, you might find just a few atoms in a whole room's volume. If there are almost no particles, there's nothing to measure, no traffic to track. The sun's energy travels through space, but there's nothing there to heat up. It's like trying to warm an empty room with a heater. If there's nothing inside, nothing gets warm. The energy just keeps going until it hits something solid, like a planet or a spaceship. That's why space stays cold, even with the sun blazing nearby. To understand why space stays cold, let's look at how heat moves. Heat always spreads from warmer to cooler areas, and it travels in three ways: conduction, convection, and radiation. Conduction is heat transfer by touch, like a metal spoon getting hot in soup. Convection is heat transfer by moving fluids, like boiling water or warm air rising. Radiation is heat transfer by invisible waves, like feeling the sun's warmth on your skin. On Earth, all three work together. The sun heats the ground, radiation. The ground heats the air, conduction, and warm air rises, convection. This system moves energy around the globe, creating weather and making life possible. But in space, things are different. Conduction needs things to touch. Convection needs air or water to move. Only radiation can travel through empty space. That's the key to our mystery. Let's dive into conduction, heat transfer by direct contact. When you touch an ice cube, your hand loses heat to the ice, making it melt. Metals are great conductors because their particles are packed close, passing energy quickly. That's why cooking pans are metal. They transfer heat fast. But can conduction happen in space? Not really. Space is a vacuum, almost no particles, so nothing to touch, nothing to pass heat along. Imagine trying to play pass the bucket with people miles apart. It just doesn't work. Without direct contact, conduction is impossible in space. Visual: hand touching ice, metal pan heating. Visual: particles passing energy. Visual: empty space, particles far apart. Visual: pass the bucket analogy. Visual: conduction x'd out in space. Visual: astronaut floating, no conduction. Visual: Earth versus space comparison. Visual: no touch, no heat. Next up is convection, heat transfer by moving fluids like air or water. Boiling water? That's convection. Hot water rises, cool water sinks, creating a rolling current. Visual: boiling pot, arrows showing movement. Heaters warm rooms this way, and it's how wind and ocean currents move heat around Earth. Visual: heater warming a room. The sun heats the equator more than the poles, driving massive convection currents in our atmosphere and oceans. Visual: global wind and ocean currents. But in space, there's no air or water, no fluid to move, no convection currents. Visual: space as empty, no currents. The sun's energy can't start a current in a vacuum. That's another reason space stays cold. Visual convection X'd out in space. Visual astronaut in vacuum. Visual no fluid, no flow. Visual Earth versus space animation. Now for radiation, the only way heat travels through space. Radiation is energy sent out as electromagnetic waves, like sunlight or infrared. These waves don't need air, water, or anything else. They travel through the vacuum at the speed of light. When you feel the sun's warmth, that's radiation energy hitting your skin and making your molecules move faster. The sun's energy travels 150 million kilometers to Earth as radiation. In space, radiation passes through emptiness until it hits something, then it's absorbed and turns into heat. That's why space itself isn't hot, but objects in sunlight can get scorching. Visual, sun's rays traveling through space. Visual, person feeling sunlight. Visual, campfire heat, infrared waves. Visual radiation hitting astronaut. Visual object in sunlight versus shadow. Visual energy waves in vacuum. Visual radiation the space traveler. Visual sun-earth connection. Let's put it all together. The sun blasts out energy as radiation, but space is so empty, there's nothing to absorb it, unless you're in the path. That's why objects in sunlight get hot, but the shadowed side freezes. Take the International Space Station. In sunlight, its surface can reach 121 degrees. In shadow, it drops to 157 degrees. That's a swing of nearly 300 degrees. Space doesn't have one temperature. It depends on whether you're in sunlight or shadow. Far from any star, space is even colder, about 2.7 Kelvin, thanks to the faint afterglow of the Big Bang. That's the true deep cold of the universe. Visual ISS in sunlight and shadow. Visual thermometer swinging. Visual sunlit versus dark side of objects. Visual cosmic microwave background. Visual deep space, cold and empty. Visual temperature depends on sunlight. With such wild temperature swings, how do astronauts survive? Spacesuits are like personal spaceships, reflective on the outside to block solar heat, with built-in cooling and heating systems inside. Tubes of water flow through the suit, carrying away excess heat or warming the astronaut as needed. The International Space Station uses insulation and radiators to manage heat. Liquid ammonia carries heat to panels that radiate it into space. It's a constant balancing act, shedding extra heat in sunlight, keeping warm in shadow. Thanks to clever engineering, astronauts stay comfortable in the harshest environment. Visual. Astronaut in suit, labeled layers. Visual water cooling system. Visual ISS radiator panels. Visual sunlight versus shadow on ISS. Visual temperature control animation. Visual engineering for survival. Visual crew working safely. So we've solved the mystery. Space is cold because it's empty, not because the sun is weak. The sun's heat travels as radiation, but only objects in its path get warm. Astronauts and spaceships need amazing technology to survive the extremes. But here on Earth, we're protected by our atmosphere, a blanket that keeps us not too hot, not too cold. Our atmosphere blocks harsh radiation, scatters sunlight, and traps warmth at night. Thanks to this, we avoid wild temperature swings and enjoy a stable climate, perfect for life. When you look up at the stars, remember, we live on a warm, wonderful planet in a vast, cold universe. Understanding why space is cold helps us appreciate just how special Earth is. Keep looking up and keep asking questions. Visual, Earth from space, glowing atmosphere. Visual, night sky, stars twinkling.